Welcome to our channel. Today, we're diving into the fascinating world of quantum physics. Get ready to explore the fundamental concepts that govern the universe at the smallest scales. You see, the world of atoms and photons doesn't play by the same rules as our everyday experience. Down there, things can be in two places at once, teleport, and even change the past. We're going to unpack these bizarre realities and their very real implications. Fasten your seatbelts, get ready to bend your minds a little, and let's unlock the secrets of the quantum realm. Imagine this, you got a beam of light, right? Classic wave ripples through the air, creates rainbows in a prism. But then, that same light acts like a barrage of tiny energy packets, photons, knocking electrons loose in the photoelectric effect. Is light a wave or a particle? Well, it's both. And it's not just light, electrons diffract and interfere just like waves too. This is wave-particle duality, one of the cornerstones of quantum mechanics. It tells us that waves and particles are actually two sides of the same coin. And trust me, we're just getting started. Let's talk about energy. In the quantum world, energy comes in discrete packets called quanta. Think of it like a vending machine. You can only buy snacks in prepackaged amounts. This quantization of energy explains why atoms are stable. Electrons in an atom can only exist at specific energy levels, like standing on rungs of a ladder. When an electron jumps from a higher energy level to a lower one, it emits a photon with a specific energy, and therefore a specific color. It's like the universe is speaking to us in this secret code of quantized energy. We've got waves acting like particles' energy coming in tiny packets, and now we're going to talk about uncertainty. Heisenberg's uncertainty principle states that you can't know both the position and momentum of a particle with perfect accuracy at the same time. The more precisely you nail down one, the fuzzier the other one gets. This isn't about our measurement tools being bad, it's about the very nature of reality at the quantum level. This inherent uncertainty has profound implications. It means that at the quantum level we have to abandon the deterministic view of classical physics. We can't predict with certainty where a particle will be in the future, only the probability of finding it in a particular place. It's a paradigm shift, embracing chance and probability as fundamental aspects of the universe. There's still a beautiful order to this quantum fuzziness, giving rise to the incredible diversity and complexity of the world around us. Get ready for one of the weirdest, most mind-bending concepts in quantum physics: superposition. It's the idea that a quantum system, like an electron, can exist in multiple states at the same time until it's measured. Imagine a coin spinning in the air. It's not heads, it's not tails, it's in this weird in-between state of both possibilities at once. The most famous example of superposition is Schrödinger's cat. Until we open the box and observe the cat, it's considered to be both alive and dead at the same time. Experiments have confirmed that particles really do exist in this superposition of states. It's only when we make a measurement that the superposition collapses, and the particle chooses one definite state. Superposition is one of the key ingredients that makes quantum computers so powerful. By harnessing the ability of quantum bits or qubits to exist in multiple states at once, quantum computers have the potential to solve problems that would take classical computers billions of years. It's a glimpse into a reality where the rules of the game are fundamentally different from our everyday experience. We're about to dive into one of the most baffling and controversial concepts in all of physics: quantum entanglement. This is the idea that two particles can be linked together in such a way that they share the same fate, no matter how far apart they are. Imagine you have two coins, and you flip them at the same time. Now imagine that these coins are linked together in a way that guarantees that if one lands heads, the other one will always land tails, even if they're on opposite sides of the universe. When two particles are entangled, they're no longer independent entities. They become part of a single indivisible system, even if they're separated by vast distances. This spooky action at a distance, as Einstein famously called it, has been experimentally confirmed time and time again. Entanglement has the potential to revolutionize fields like communication and computing. Imagine being able to send information instantly, regardless of distance, using entangled particles. Entanglement is a powerful reminder that the universe is interconnected in ways that we're only beginning to understand. Let's talk about the wave function, the unsung hero of the quantum world. It's not a physical object you can touch or see, but rather a mathematical description of a quantum system. The wave function doesn't tell you exactly where a particle is, but rather gives you a probability distribution of finding it in different locations. It's not that we just don't have enough information. The particle literally doesn't have a definite location until we measure it. Imagine the wave function as the conductor of a vast invisible orchestra. Each instrument represents a possible state of the particle, and the volume of each instrument corresponds to the probability of finding the particle in that state. When we make a measurement, it's like shining a spotlight on the orchestra. Suddenly, all the instruments except one go silent, and we're left with a single definite note, the outcome of our measurement. This is what's known as wave function collapse. The wave function and its probabilistic nature are central to understanding the bizarre behavior of the quantum world. We've talked about the wave function, the mathematical description of a quantum system. Now let's meet the equation that governs its evolution over time, the Schrödinger equation. Think of it as the instruction manual for how the wave function, that cosmic sheet music, unfolds. It's like Newton's laws of motion, but for the quantum world. It tells us how the probability distribution of a particle's state changes over time, influenced by forces and interactions. The Schrödinger equation is a powerful tool. It allows us to predict how atoms will behave, how electrons will move in a molecule, and even how light will interact with matter. While it might not predict the future with absolute certainty, it gives us a powerful glimpse into the quantum world. Imagine a crowded subway car. Each seat represents a unique quantum state that an electron in an atom can occupy. The Pauli exclusion principle says, no two fermions, particles like electrons, can occupy the same quantum state at the same time. Electrons, being fermions, are extremely picky about their seats. They each need their own unique set of quantum numbers, which describe their energy, angular momentum, and spin. This principle is why atoms don't just collapse in on themselves. Electrons, forced to occupy different energy levels, create a sort of scaffolding that gives atoms their size and shape. The Pauli exclusion principle is also responsible for the incredible diversity of the periodic table. Imagine you're trapped in a room with walls so high you could never climb over them. Classical physics would say you're stuck, but in the quantum world, there's a chance you might just tunnel right through those walls. That's quantum tunneling. It's like the particle borrows energy from the future, momentarily breaking the rules of classical physics to slip through a barrier it doesn't have enough energy to overcome. Quantum tunneling is essential for life as we know it. It's how the sun fuses hydrogen into helium, releasing the energy that bathes our planet in light and warmth. Tunneling also plays a crucial role in electronics. Without quantum tunneling, our digital world simply wouldn't exist. We've explored some pretty mind-bending concepts, but here's the thing about quantum physics. It's not just theoretical. It's the foundation for countless technologies that shape our modern world. Take lasers, for example. They rely on the quantum phenomenon of stimulated emission, where photons interact with excited atoms to create a beam of light that's both powerful and coherent. Lasers are everywhere, from barcode scanners to fiber optic cables to medical imaging devices. But perhaps the most exciting frontier in quantum technology is quantum computing. By harnessing the bizarre properties of superposition and entanglement, quantum computers have the potential to revolutionize fields like medicine, materials science, and artificial intelligence. From the smartphones in our pockets to the medical devices that keep us healthy, quantum physics is more than just a theory. Thanks for watching. If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating insights into the world of physics. We've only scratched the surface of quantum mechanics, but I hope this journey has sparked your curiosity about the hidden workings of the universe. It's a strange, counterintuitive, and utterly fascinating world down there, and it's full of mysteries waiting to be unlocked. Let us know in the comments which quantum concept you'd like to learn more about. Until next time, keep questioning, keep exploring, and never stop looking up at the universe with wonder.